You tap play and a film begins almost immediately. No disc, no giant download, no obvious waiting. Just a screen lighting up with video as if the file was somehow already there, hovering invisibly in the room, waiting for you to ask for it. That everyday moment is so smooth that it hides how strange it really is. Because a streaming service is doing something very hard, it is taking a massive video file, delivering it across networks to millions of people, and doing it quickly enough that it feels effortless. So what actually happens when you press play? Where is that video coming from? Why does it usually start so fast? Why does the picture sometimes get blurry and then sharpen again? And why can something that feels so simple depend on such a huge amount of hidden infrastructure? In this video, we are going to follow that path clearly and simply, because streaming is not just entertainment, it is a delivery system. And once you see the system behind it, pressing play starts to look a lot more impressive. The first thing to understand is that a streaming service is not sending you one giant movie file from beginning to end all at once. Instead, the system is designed to start playback quickly and then keep the next parts of the video arriving just ahead of what you are watching. Modern HTTP streaming systems, such as HLS, are built to work over ordinary web infrastructure and adapt playback to changing network conditions rather than relying on one single static delivery path. That is why streaming feels different from old-fashioned downloading. With a traditional download, you often wait for a large file to arrive before you can really use it. With streaming, the service tries to get just enough video to your device so playback can begin, then keeps feeding the rest of the content forward in a steady flow. From the viewer's side, that feels instant. From the system's side, it is a constant balancing act. Long before you ever press play, the platform has already done a great deal of work. A streaming service usually starts with a high-quality source version of the film or episode. But that source is not practical to send in exactly the same form to every viewer. A phone on a weak mobile connection, a laptop on cafe Wi-Fi, and a large television on strong home broadband do not need the same version of the same video. So the platform prepares multiple versions of the content at different sizes and bit rates. In practice, this is done through encoding and transcoding workflows, and adaptive streaming systems commonly produce several renditions, so the player can switch among them later depending on conditions. AWS Media Convert, for example, explicitly supports adaptive bitrate packaging and automated ABR output ladders for streaming delivery. That step matters because streaming is not really about giving everyone the best version in abstract terms. It is about giving each viewer the best version their situation can support at that moment. If your connection is strong, the service can deliver a sharper, higher bit rate version. If your connection weakens, the service can shift to a lighter version that keeps playback going. That flexibility is one of the reasons streaming works as well as it does. After the video has been prepared in multiple qualities, it is usually broken into small pieces. This is another hidden part of the process that makes streaming feel much smoother than people realize. The player is not normally requesting one enormous file from start to finish. It is requesting a sequence of smaller media segments, guided by a manifest or playlist file that tells the player what versions exist and where the next pieces can be found. Apple's HLS system is built around exactly this model. Playlists describe media streams, and the content is delivered over ordinary web protocols in smaller segments. That design solves several problems at once. It helps playback start quickly. It makes it easier to switch quality levels without restarting the video. And it gives the platform a much more flexible way to move content across the internet. This is where the story gets even more interesting, because the internet path itself matters just as much as the video file. If every person had to stream every show directly from one central location, the whole system would be far slower and far more fragile. The distance would be greater, the traffic load would pile up in fewer places, and busy periods would create much worse bottlenecks. So streaming platforms rely heavily on content delivery networks, usually called CDNs. A CDN is a distributed network of servers that stores or caches content closer to users. Cloudflare describes a CDN as a geographically distributed group of servers that caches content near end users, so content can be delivered more quickly and with less strain on origin systems. This is one of the biggest hidden reasons streaming feels fast. The film you're watching may not be traveling all the way from one faraway master server every time you press play. A copy, or at least a large amount of the useful delivery material, may already be much closer to you inside a regional cache or edge server. That shorter path makes a huge difference, and some major streaming services push this idea even further. Netflix's Open Connect system is a good real-world example. Netflix describes Open Connect as the global network responsible for delivering Netflix shows and films, and says its goal is to localize Netflix traffic as close as possible to members, including inside ISP networks and at internet exchange points. So when you press play, your stream may already be much closer to you than you think. That does not mean the video is in your TV already, but it does mean the delivery path has often been shortened on purpose so that the service can respond faster and more efficiently. Now we get to the player itself, which is doing more active decision-making than most viewers realize. Once playback begins, the player keeps checking how well the connection is holding up. If bandwidth is plentiful, it can ask for a higher quality version of the next video segments. If conditions get worse, it can step down to a lower bit rate before the stream stalls completely. AWS's documentation for adaptive bitrate streaming states this directly. The player device adjusts which rendition it downloads based on available bandwidth, switching higher or lower as conditions change. Apple's HLS documentation also emphasizes dynamic adaptation for changing wired and wireless conditions. That is why the picture sometimes gets softer for a moment and then sharpens again. It is usually not random. The player is trying to preserve continuity. In most cases, a brief drop in image quality is far better than a full pause. And that brings us to buffering. Buffering is what happens when the next chunks of video do not arrive quickly enough to stay ahead of playback. The player usually keeps a small reserve of upcoming content, but if that reserve shrinks too far, the stream has to pause and wait. From the viewer's side, buffering feels like failure. From the system side, it means one part of the chain has stopped keeping up. That weak point could be your home Wi-Fi. It could be a crowded broadband connection. It could be a temporary slowdown between your internet provider and the nearest cache. It could be congestion farther upstream. The important point is that buffering is not just the app being bad. It is often the visible result of strain somewhere along a much longer delivery path. The basic architecture of streaming systems makes this clear. Playback depends on ingest, processing, origin, delivery, and client behavior all working together. This is also why streaming feels so deceptively simple. The app on your television is only the visible surface. Behind it sits a chain that includes stored source media, encoding systems, segmented delivery formats, CDN caches, peering and ISP relationships, home broadband, local networking, and player software making real-time decisions. Once you see that full path, pressing play starts to look much less like opening a video and much more like activating a large delivery network built for motion picture files. That hidden chain matters because every part of it changes the final experience. If the content is poorly prepared, the stream will not adapt well. If edge caching is weak, delivery paths get longer and slower. If the home network is unstable, even a very strong service can feel unreliable. And if the player cannot respond well to changing conditions, the viewing experience becomes much more fragile. So the smoothness people associate with great streaming is not just a product feature. It is the result of many different systems cooperating successfully. And that is what makes streaming such a perfect hidden infrastructure topic. It feels weightless, even though it depends on very physical systems. It feels immediate, even though the content has been carefully prepared in advance. It feels simple, even though what is happening underneath involves storage, encoding, caching, transport, and adaptation. By the time a viewer sees a clean progress bar and hears the first line of dialogue, a remarkable amount of hidden work has already happened. A master file has been processed, multiple versions have been created, the content has been broken into smaller pieces, those pieces have been placed where they can be reached quickly. The player has chosen a version it believes your connection can handle. And the stream has begun moving through the internet in a form designed to stay just ahead of your eyes and ears. That is the infrastructure behind streaming services, not just entertainment. A carefully engineered delivery system, not just a media app. A layered network of preparation, storage, transport, caching, and adaptation built to make massive video files feel instant. And like so many hidden systems, the better it works, the easier it is to forget that anything extraordinary is happening at all. If you enjoyed this video, make sure to like and subscribe to Hidden Infrastructure of the World. Also, comment down below what hidden infrastructure you want to see next. See you in the next video.